In this video, we are going to compute one more flux of a vector field, and this one is very simple. So it only has the kth component, so x and y components are zeros, and then we just have z. Okay, so we want to compute it over the upper hemisphere. Z equals square root of 64 minus x squared minus y squared. Okay, so the first thing that we need to do is find the partial derivatives of this thing. And generally, that's what you would have to do to compute flux. So you would take the force and dot it with negative gx, negative gy, and 1. However, in this particular case, because the force already has zeros and two zeros for the x and y components, when you compute the dot product, you're not gonna need the gx and gy because you're multiplying them by zero. So I'll just leave them like this. We do not need them. This is a simple problem because 0 times anything is just going to be 0, so I don't care what it is. And then we'll just have a z. However, z cannot be left as z because this is a surface integral. So on the surface, z equals that square root. So this is going to be square root of 64 minus x squared minus y squared. And that's what we're going to need to integrate. Now, over what? Well, the projection of a hemisphere on the xy plane is just a circle. And the fact that it's 64, you have a circle x squared plus y squared equals 64 that has a radius of 8. So we just have to set up this integral in polar coordinates of this square root. Okay, so what happens when we switch to polar coordinates? So think of this as 64 minus r squared, right? Because in polar coordinates, x squared plus y squared is r squared. Okay, so now you're integrating over the whole circle, right? Including the inside. So on the circle, x squared plus y squared equal 8, but you are not integrating over the boundary. You're integrating over everything inside. So here you have to leave it as r squared. So here we got 64 minus r squared. So we're switching to polar. And the integral, very simple, 0 to 2 pi, because this is the whole circle. And this one is going to be 0 to the radius of the circle, which is 8. However, there is one extra thing that hopefully you didn't forget, and that is an extra r that comes out from switching from rectangular to polar. So we call this the Jacobian, and that's an extra r. I'll just place it in front of the square root. Okay, now we do want to compute this integral, and this integral is splittable, meaning that because it has no theta, we can just separate the theta integral from the r integral and multiply them. And so this is going to be square root of 64 minus r squared r dr. Okay, so let's first concentrate on just because this one is going to be 2 pi, let's concentrate on the r integral. And at first I'll just drop the limits and compute the indefinite integral. Now, this indefinite integral, and hopefully everybody knows that this is not 8 minus r, like you cannot separate the square root at a minus. That does not work. What you do instead is think of this whole thing as u. So this is a u substitution. And this is going to become 64 minus r squared. Now let's compute du, which is derivative of u. Now, derivative of 64 is 0. Then we're going to have minus, which is very important. Derivative of r squared is 2r dr. All right, so solving this for dr, we're going to divide both sides by negative 2r, which is going to cancel this here. And so this is going to just become du over negative 2r. Okay, so let's switch this. So r is going to stay for now. And then we'll have square root of u. And then dr becomes du over negative 2r. Now notice here how r is going to cancel out, right? So if you actually forgot that r, that would be really bad, because then this integral would be much harder to compute. You would actually have to probably perform like a trigonometric substitution or something like that. This would be very difficult. But because there is an extra r, and that's the Jacobian that comes out of switching to polar, you are able to convert this to a pretty simple integral. And let's not forget that the negative 2 did not cancel, and it was on the bottom. So this will become negative 1/2. Now, how do we integrate square root? Integrate, not differentiate. So think of square root as a power 1/2. So hopefully you know that square root is responsible for power 1/2. How do we integrate a power? Well, we add 1 to the whatever power we got. So we're going to get u to the power 1/2 plus 1, which is like 1/2 plus 2/2 or 3/2. And then we need to divide it by the same thing. So we divide it by 3/2. Now, I am not going to put plus c just because it's actually definite integral, so I will be substituting the limits in a second, but we still want to simplify. So dividing by 3/2 is the same as multiplying by the reciprocal of it, which is going to be 2/3. And the u to the power 3/2 is still there. So I can see that 2 and 2 here cancels out. Now, I always go back to the original variable. So there are two ways that a substitution can be done. You can possibly switch the limits to the new variable and then substitute those, but I don't like that. I am going to switch all the way back to r. So I remember that I called u 64 minus r squared. So this is going to become 64 minus r squared to the power 3/2. So I am done with my integration, and now I can substitute the limits. So let's go ahead and do that. So I got negative 1/3. Then I got 64 minus r squared to the power 3/2. And I need to substitute 0 and 8. Okay, so first I substitute 8. Remember, the top limit is first. So that is going to become 64 minus 8 squared, 3/2. Then I'm substituting the bottom limit, but I'm subtracting. So that would be negative 1/3. 64 minus 0 squared is 0, 3/2 power. Okay, now what happens to the first term? So 64 minus 64, that's just 0. The two minuses become a plus, 1/3. 64 minus 0 squared. Okay, so that's just going to be 64 to the power 3/2. Now, at this point, you can use a calculator, or maybe you do know that when we take that 64 to the 3/2, this is the same thing as square root of 64, which is 8, and then you cube that. Okay, now, I don't know if they need us to simplify that. We could. Okay, so that's 512. So we got 512 divided by 3. That's our integral. But we still have to remember that we also had this 2 pi there, right? And so that looks like that's going to be my final answer. So let me multiply the 512 by 2. So that gives me 1024. I don't know if I can divide this by 3. No, so it's not. Doesn't look like that's going to be possible to simplify this. So this is just going to be that. All right.